Okay, I've got a few examples here to show you how to actually calculate volumes of three-dimensional solids of revolution using disk. So the first example we'll look at is to find the volume of the solid obtained by rotating the region about the given axis. So those will be the instructions for every example in this video, so I'll just reuse those. So example 1, the region will be bounded by y equals the square root of x, y equals 0, so we've got this curve, this horizontal line y equals 0, and the vertical line x equals 4, and we're going to rotate around or revolve around, let's see, the x-axis, okay? So I'm going to do an example rotating around the x-axis, then I'll do an example rotating around the y-axis, and then we'll rotate around an axis that's neither of those, okay? So first thing we need to do is kind of draw a picture of this region, think about rotating it, cutting it into disk, and then adding all those volumes together. So y equals the square root of x around the x-axis. So the square root of x, we're going from y equals 0, so this is the y equals 0 line. We need the x equals 4 line, which is this line here, right? We need the curve y equals the square root of x, which looks something like this. And so the region that we're rotating, is this region here. And we're rotating it about the x-axis, which happens to be the line y equals 0, okay? So this is what we have. Now, we could, and so this is y equals the square root of x. So what we need to do now is create the three-dimensional solid and look at what one disk looks like, okay? So our three-dimensional solid, I'll sort of go over this in black. That's terrible. Let's see here. So I want to mirror this distance, so yeah, that looks okay. The hard part is getting the curve to look similar. Okay, so something like that. That's our solid, just about. I'll get rid of this guy now. We still know that that's 4, okay? And on the end, it's going to be a circular cross section now. So that's our three-dimensional solid. And what we need to do is we need to look at what one disk looks like. So I'm going to pick a slice that's perpendicular to my axis of rotation. So it's going to be a vertical slice. I'll pick it right there maybe. And then I'll choose the point directly above and directly below. And then I get my infinitely thin disk that looks like this, okay? So the thickness of this disk is dx. It's a horizontal thickness. My radius measures from this line up to this curve. I don't want to measure my radius from this line down to here because this was a mirror image of the original function. So I want to use all the original pieces to measure my radius. So my radius is right there, okay? All right, so now let's set up the integral. I've got an infinite number of these disks, right? I've got an infinite number of these disks. And so when I look at my integral, my volume is going to be an integral of pi times my radius squared, right, times the thickness of the disk, which is dx. So that means that my limits of integration have to be x values, and I can tell that I'm going from 0 to 4. And the only thing left to do is to write my radius in terms of x, okay? So my radius here, let's go over here and write our radius. The radius is a vertical measurement, so it's going to be my top y value minus my bottom y value. Okay, my top y value minus my bottom y value, and they have to be in terms of x. So my top y value is dictated by the curve y equals the square root of x. So my top y value is just the square root of x. Minus my bottom y value, well, that's just 0. It's constant all the way across for any disk that I choose. So my radius happens to be the square root of x. So I'm going to rewrite my integral, pull my pi out. So I got pi, since it's a coefficient, times the integral from 0 to 4 of my radius, which is the square root of x, quantity squared, dx. So this integral represents the volume of that three-dimensional solid. It's adding all of the disk volumes together from 0 to 4 that are infinitely thin, giving me the volume of the solid. So now I'm going to go ahead and work out the integral. I'll speed the video up to get to the end. I'm not going to focus on how to do the integral, but you can double check your answer with me momentarily. Okay, so when we evaluate the integral, we can see that the volume of that bullet-looking shape happens to be 8 pi once we evaluate the integral. Okay, let's move on to another example where we rotate around the y-axis. All right, so example two is the region bound still by y equals the square root of x, okay? But it's bound by that along with the line x equals 0 and the line y equals 3. And now we're going to rotate around the y-axis, okay? So let's get an idea of what this looks like. We know we're rotating around the y-axis, which is here. And again, y equals the square root of x. You know what, let's move our x-axis down since we're rotating around the y-axis. I don't need so much. Y equals the square root of x looks something like that. Y equals 3, let's say is right here. So it's this line. So the curve will intersect that line. And x equals 0 is right here, this vertical line. So this here is the region that we're rotating around the y-axis. So now let's try to draw the three-dimensional solid, cut it into disk. So our solid, I need to draw a mirror image of this guy over here, the best I can. Just do the best you can. Okay, so we have that, and then on the top I'll have a circular cross section. It's kind of long. Okay, so we have something like this. So we have this, maybe it's kind of like a top or something that you would spin. It's got this point at the bottom, it opens up. It is a solid, it's not hollow, right? So now we have to create a slice. Now our axis of rotation is vertical, so our slices have to be horizontal. So I'll pick somewhere between here and between 0 and 3 to slice. Now I'm doing a horizontal slice, so I need to locate a point to the left, and a point to the right. And then draw an infinitely thin disk, something like that. Now the thickness of this disk is dy, it's a vertical measurement. The radius measures from my axis of rotation to my original curve, which is going to be to the right. So that's my radius, okay? And I know my radius is going to have to be in terms of y. So how do I calculate a horizontal radius? Well, the radius here is going to be the rightmost x minus the leftmost x. And those have to be in terms of y, since my thickness is dy, and I know I have to integrate. So my rightmost x is dictated by the curve. Now what was the curve again? It was y equals the square root of x. Okay? I need my rightmost x to be in terms of y. So that means I need to solve this for x, right? I need to know what x is because I need x values here, but they're written in terms of y. So this guy, if I square both sides, I can see that x is the same thing as y squared. X is the same thing as y squared. So my rightmost x is y squared, right? And my leftmost x is x equals 0. It's constant. No matter what disk I choose, it's 0. So my radius is y squared. So now to get the volume, I will take the integral. I already know I can factor out my pi times the radius, y squared, squared, times my thickness, dy. So this is the sum of all of the disk volumes, thus giving the volume of the entire solid. Now I'm integrating with respect to y, so I need y values here, and clearly I'm going from 0 up to 3. From 0 up to 3. So this integral represents the volume of that solid. Again, I'll speed up the video while I work out the integral, and then you can check your answer if you want to work along. Okay, so it looks like when we evaluate the integral, we get 243 pi over 5, and that represents the volume of this sort of interesting three-dimensional solid. All right, now let's rotate around an axis that's not the x or the y-axis. So now, let's rotate the curve. Y equals the natural log of x, bounded by that curve, bounded by the line x equals 1 and y equals 4. And let's rotate around the vertical line x equals 1. Okay? So let's try to draw a picture of this. So y equals the natural log of x, just real quick, remember, looks something like this. It's approaching the y-axis. The y-axis is an asymptote. That's our curve. Then we've got the line x equals 1. Now, whenever x equals 1, the natural log of 1 is 0. So this point right here happens to be where x is 1. So that's our vertical line, x equals 1. Okay? And we've got the line y equals 4, so eventually this curve is going to come up and hit the y value 4. So there's our line y equals 4. So we can see that the region we're looking at is this region right here. This region right here. Okay? And so now let's kind of get rid of all the other clutter. We don't need any of this other stuff now. Okay, and so that's the region we have, and we're rotating around the line x equals 1. So our axis of rotation here is this line. We're rotating around this guy. So now we have to be a little more careful. We have to be a little more careful. In fact, I'm going to make my y-axis a dashed line because it's not really terribly important anymore because we're not rotating around it. We're rotating around x equals 1. So now what we're going to do is take and draw our three-dimensional solid. So I'm going to draw a mirror image across here. So I'll sort of approximate that distance to draw my top point. Maybe it looks like this, and then maybe like that. And then I have a circular cross-section on the top. So that's my solid. It's very similar to the shape we just had in the last example, except now it's rotated around the line x equals 1. So now I need to create a perpendicular cross section to my vertical axis of rotation. So that's maybe choose right here, just like before. Pick the point immediately to the left and to the right, and draw the infinitely thin disk that goes through right there, whose thickness is dy. Now let's look at the radius. That's always the key here. The radius is this distance. That's terrible. The radius goes from the center, the axis of rotation, to the original boundary. So don't go to the left, go to the right. So this is the radius of this disk. And in this case, since the radius is measured left to right, we have to take the rightmost x minus the leftmost x. And we know we're going to integrate with respect to y, so I need those in terms of y. So this curve, the x value on the right, is dictated by the curve, which is y equals the natural log of x. And I need to know what x is over here, so I have to solve it for x. Now to undo a natural log, you do a base of e on both sides. So e to the y equals e to the natural log of x, and those cancel, so we can see that x is e to the y. So that means that my radius is going to be, my rightmost x is going to be e to the y. Minus my leftmost x now is the constant, not 0, but 1. So now my radius is e to the y minus 1. And that's the big difference when you're not rotating around the x or y axis. You're going to have to measure from a constant that's not 0. So you got to be really careful with that. That's why I'm always emphasizing this idea for measuring radius. Always think right minus left or top minus bottom if it's vertical. Okay? All right, now setting up the integrals, a piece of cake. So we need to do pi times the radius squared times the thickness, and we need to add all of those together, factoring out the coefficient of pi, and we need to integrate with respect to y, so we need to add from what y value to what y value. Well, we're clearly going from 0 to 4. 0 to 4. And there we go. That's the hard part. That integral represents the volume of that solid. I'll go ahead and work it out, and you can come back and work it out too and see if you get the same answer. Okay, so I do want to take a second to talk about the integration here. When we multiply e to the y minus 1 by itself, make sure you understand why we get e to the 2y minus 2e to the 1y plus 1. Okay, so that's the first thing. Then when we want to integrate this, we do it term by term. We do the antiderivative of each term. Now remember, this is a y, not a 4. And so the antiderivative of the last two terms is very simple. The antiderivative of the first term, though, you may need to use substitution if you can't tell that you should get 1/2 e to the 2y. So you'd let u be 2y, and you should see that du equals 2 dy, so dy equals 1/2 du. And so that's where this coefficient of 1/2 comes out. You can work on that on your own. But then when you evaluate, you get these e to powers, so we can't really simplify it too much. Okay, so that represents the volume of this solid that's rotated around a non-x or y axis. Let's do one more. That was example 3, by the way. Forgot to number that example. Sorry about that. And this will be example 4. Okay. So example 4, look a little bit different than the others. Let's say we have the region bounded by x equals y squared plus 1 and x equals 3. So we've got this curve and this line creating a region, And let's rotate it around the line x equals 3, okay? So we need to sort of draw this out. X equals y squared plus 1 is a parabola, but it's horizontal. So if we were to graph it out, x equals y squared plus 1. If we plug in 0 for y, then x is 1. So here's 1, and y is 0. If we plug in 1 for y, then x is 2. So there's 2, and we plug in 1 for y, then we get this point. But we could also plug negative 1 in for y and get x equals 2. So we get this point here. And so you can start to see it's a parabola opening to the right, basically. So it looks like this. So that's our curve, x equals y squared plus 1. And we want the region bounded by that curve in the line x equals 3. So here's our line x equals 3. And so what we're looking at is this region right here. And we're rotating it around the line x equals 3. Okay? So let's see if we can draw the solid and look at a disk. So now I need a mirror image of this curve over here. So maybe goes out to there. So something like that is our three-dimensional solid. And now we need to slice it horizontally since we have a vertical axis of rotation. So let's say we slice it right here. So we'll create the left and right sides of our disk, our infinitely thin disk, which looks something like this. The thickness of which is dy, since it's measured vertically again. And now the radius we need to measure from the axis of rotation. We have two choices. We can go to the right or we can go to the left. Now remember what I've said in the other examples. You always want to measure from your axis of rotation to the original curve. So in this case, we're going to measure our radius to the left. So we'll call that r. So now we can see that the radius is the right. You always do the right minus the left to get a positive radius, a positive number. The rightmost x is 3. It's a constant 3. Minus the leftmost x has to be in terms of y. Okay? So remember, the leftmost x is dictated by the curve, which is the equation x equals y squared plus 1. So the leftmost x is y squared plus 1. It's that simple. So 3 minus the quantity y squared plus 1. So that's our radius. So to get the volume, we need to do the integral of pi times the radius squared. Now let's go ahead and clean this up a bit before we write it squared over here. So I'll distribute my negative. So I get negative y squared. 3 minus 1 is positive 2. So that's my radius, okay? So pi times my radius squared times the thickness of the disk dy. And since I'm integrating with respect to y, I need to put limits of integration that are y values. And so we need to know, remember, the 1 and negative 1 were not for this point here. I need to know this y value, and I also need to know this y value. So how do we do that? Well, this y value is where this curve and this line intersect. So what I need to do is figure out where they intersect. So what I'll do is I know that x equals y squared plus 1 and that x also equals 3. So I need to solve the equation where the x's are equal. In other words, where 3 equals y squared plus 1. And when I solve that, it's going to tell me, it should tell me both of these y values on our graph. So if I solve this for y, I'll subtract 1 to get 2, and then take the square root of both sides, and I get plus or minus the square root of 2. So this guy is negative square root of 2, and this guy is positive square root of 2. Okay? So that means my limits of integration here will be from negative square root of 2 to positive square root of 2. And so this integral represents the volume of this interesting solid of revolution. I'll work the integral out, and you can come back and check. All right, so I knew I was going to need a lot of room to do this integral. Not that it's difficult, but a lot to show. And when you get all the way through, you end up getting 64 pi square roots of 2 over 15 for your volume. Now, I did some simplifying here that you could stop at any point, perhaps. Maybe you could stop at this point and call it done, that's fine. But all of these had square root of 2 in the numerator, so I thought a common denominator would be good. And it actually cleaned up pretty nicely. So that's finding volumes by disk. Hope you find it interesting. You'll enjoy aspects of it. You might get frustrated. The hard part most of the time for students is drawing the graphs. They're sometimes not as proficient with the graphing. So take your time, maybe set up XY tables, find intersection points that can be useful, but make sure you get the graph right, and then get an appropriate cross section that's perpendicular to your axis of rotation. That's really important. After that, make sure you mark your radius properly and either do right minus left if you're horizontal or top minus bottom if you're going vertical, and make sure it's in terms of the right variable based on dx or dy. Go practice, have fun, and good luck.